Hello, new Orgo students. It's Eric, Sam, and Roos here to give you all a brief lesson on resonance and how it applies to your future in Orgo. Resonance is a concept you should all be familiar with from Gen Chem, so let's launch into it by going over what you should know from Gen Chem, even if you don't remember.
First of all, I would like to start by giving a quick definition of resonance. It's the idea that electron pairs, as lone pairs or in pi orbitals, can be delocalized within a molecule, giving different formal charges to specific atoms while preserving the overall charge of the molecule. We're going to start by looking at an ozone molecule shown here, with 18 valence electrons. First, I'm going to label the oxygens as 1, 2, and 3. This will help show that while these two molecules may look different, in terms of structure and arrangement, they are the same. Only electron density has changed. Now if we push electrons around a bit, we'll see how the formal charge of each oxygen can change, while the overall charge stays the same. So we'll start with this lone pair on oxygen number 3. It'll move down to form a double bond with oxygen number 2, while the electrons in this pi bond right here will move up to oxygen number 1. Notice how throughout this change, the plus charge has stayed on oxygen number 2, while the negative charge has switched from oxygen 3 to oxygen number 1. This delocalization of charge and electron density explains why each bond length is approximately 1.28 angstroms. This is instead of having varying bond lengths for a single bond and a double bond.
This is generally where Gen Chem leaves you as far as resonance goes. So to get you all up to speed on what you need to know for Orgo, we're going to take a look at these atoms from an orbital perspective for a second to show how resonance and orbitals go hand in hand. Normally, oxygen has its 1s orbital completely filled, its 2s orbital completely filled, but only two of its three 2p orbitals filled. Therefore, you can draw the three oxygen atoms of ozone next to each other and see that the empty p orbitals all line up within a single plane. And it's very hard to do in terms of drawing this in this 2D space, but if you were to imagine there's a plane sort of bisecting these molecules, all of these p orbitals would be in a line with each other in 3D space in the same plane. So now you can add in the single bond of ozone and just leave that be because sigma bonds are not involved with resonance at all. They are just locked in. You can free rotate around them, but that has nothing to do with resonance. So there's 4 of your 18 valence electrons gone as well. Now you're also going to have lone pairs in this molecule that are not planar with the p orbitals that we've drawn in here. So just take my word for it, but these in 3D space would all not be planar with these p orbitals. So you've got another 10 there. So that's 14 of 18 valence electrons taken care of. The 4 final valence electrons form 2 lone pairs that are shared by the 3 empty p orbitals to guarantee that all 3 oxygens have full valence shells. This creates a single cloud of electron density, since the empty p orbitals all line up in the same plane. Since there are only 2 electron pairs to fill the 3 orbitals, the molecule is always neutral, while individual atoms constantly change charge as the electrons occupy different orbitals and swap between resonance structures. The 3 p orbitals act as a conduit for the 4 pi electrons to be shared amongst all 3 atoms, which translates to the 2 Lewis resonance structures we just drew. So in this case, these two, this valence pair, could form the pi bond there, which will be the double bond, while these other two will then go over here, giving this a net negative charge and a full shell, this a net positive charge and a full shell, and this a neutral charge, and that's the one resonance structure. The other one, of course, would be flipped around. So this orbital perspective is another way to define resonance, and one that will be useful to think about in terms of looking at reaction mechanisms and looking at how electrons move around, which is a very important concept in the weeks to come.
With a sound knowledge of the basic concepts of resonance in hand, we will now look at some carbonyl compounds which will show how resonance dictates where reactions will occur on a molecule. This is the basis of what you do in Orgo, so you can probably see why this is an important concept in terms of Orgo as a whole. Now, these compounds are generally not seen in Orgo 1, but we feel that they are good examples of how resonance works in general. Here we see the reaction of a ketone molecule with a standard nucleophile, in this case a cyano group. A nucleophile is simply an electron-rich molecule willing to donate a lone pair to form a bond. In terms of electron pushing, it is better to have a negative charge on a more electronegative atom, such as the oxygen, so we can push the double bond up towards the oxygen. As we do this, this gives the resonance structure shown over here, with a full positive charge on the carbon and a full negative charge on the oxygen. Also, there is already a dipole moment in this molecule due to oxygen's electronegativity. Therefore, there is already a partial positive charge on the carbon and a partial negative on the oxygen. This makes it more natural for the pi electrons to flow towards the oxygen, as shown in this resonance structure. This also shows how when the carbon gets its positive charge, it is then attacked by the negatively charged nucleophile, as a negative always attacks a positive. This is a great example of how drawing resonance structures can aid in reaction mechanisms and figuring out a hypothetical product. The product we have here has an O-, which will then bond with a hydrogen ion in its environment to form an alcohol group.
This resonance also helps on the other side of the spectrum, in terms of stabilizing a negative charge. If we look at this molecule here, it's also a ketone, but instead of a generic R group coming off the carbonyl group, we have an ethyl group, which is just a 2-carbon group. Now, this ethyl group, these carbons, there is going to be, or are going to be, protons on these chains. Now, this methyl group carbon, these CH bonds up here, are going to have a pKa of about 50 because they do not have any resonance stabilization, and therefore there's no way for them to be broken very easily. However, due to the stabilization provided to the conjugate base, should a base like hydride anion attack this hydrogen and abstract it, we would get this here, which is then resonance stabilized here. So because this structure can form, the pKa of this methyl group right here that is 1 carbon away from the carbonyl carbon, that pKa is 19.2. So as you can see, resonance is very helpful in terms of identifying what are strong acids, strong bases, weak acids, and weak bases, because the general rule is delocalization equals stabilization. Now from these resonance structures, 2 things could happen. This oxygen, like we saw last time, could just abstract a hydrogen, reform the base, and make an alcohol group right here. And that can happen. However, what could also happen is this oxygen could push through to here and reform its double bond like seen there, and then this double bond would then push out and attack any nearby electrophile, should there be one in solution, which would then bond there and form a new C2 electrophile bond. So this is a very useful technique to know, and it's very useful synthetically. And that, again, is all just based on the fact that resonance structures can be created. So even in this case, resonance is still the most important thing.